All right, everybody, let's look at a computational example. So what we've got is the vector space of all polynomials of degree less than or equal to 2 with real coefficients. So we'll call that vector space P sub 2. And so one question that we can answer is, does this set t squared plus 2, 2t squared minus t plus 1, t plus 2, and t squared plus t plus 4, does this set span P sub 2? Well, if we take the coefficients a, b, c, and d that are just real numbers, then if we take the linear combinations of those things, we get an expression that looks like this, kind of combining terms with our powers of t, gives us a plus 2b plus d t squared, plus a negative b plus c plus d times t, and 2a plus b plus 2c plus 4d. Well, we can kind of take this a, b, c, and d as a four-dimensional input, and if we multiply by kind of the matrix of these coefficients, we get 1, 2, 0, 1, 0, negative 1, 1, 1, 2, 1, 2, 4 times this vector a, b, c, d gives us our coefficients that we would have for our t squared, our t, and our constant. Now, kind of to answer that original question, does this span the space? Well, if we take that matrix 1, 2, 0, 1, 0, negative 1, 1, 1, and we would take that thing and reduce it down to row echelon form, then we're going to get a matrix that looks something like this. So we've kind of got the identity matrix. We don't have any zero columns. And so when we see this, because this thing doesn't have any zero rows in it, then that really tells us that yes, it is going to be possible to span the entire space of polynomials with that collection of vectors. So reduced row echelon form kind of gives us the indication for that. Well, kind of taking this one step further, if we just take this matrix T, kind of representing this linear transformation, to be this matrix 1, 2, 0, 1, then if we could find some matrix M such that T times M gave us this reduced row echelon form, then what this does is it really gives us an easy way, kind of an immediate way of solving, well, what does A times X equal to 1, 0, 0? Well, that tells us that it's just 1, 0, 0, 1. Or 1, 0, 0, 0. If we have a times x being 1, 0, 1, then that gives us 0, 1, 0, 0 is a solution for that. ax giving us 0, 0, 1 means that we can have x be 0, 0, 1, 0. And so kind of putting this into like a parallelized notion, if we take our matrix A times, so remember this is our reduced row echelon form, so we take that thing times this matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, then that thing gives us the 3 by 3 identity matrix. And so if we can find some matrix M, so that T times M times this matrix that we have here giving us the identity matrix, then this M times that matrix almost acts like the inverse. Not quite like the inverse, because remember, this thing is not square. And so things are not necessarily one-to-one or onto. And so it may not quite be the inverse, but it may get us close. Let's see what we can do. So the question of how can we find M in this case, well, the answer is that we can do our row operations on the transpose of T. So T transpose gives us this. And our row operations, remember that we can represent our row operations as a matrix multiplication. So if we have this matrix Y, so for doing, well, how do we come up with this matrix Y? Well, we say that we want to take the first row times -2 and add it to the second row. So we take the first row times -2, add it to the second row, and there's our entry for that row. For the first one, we want to leave that row alone, so it just looks like the identity matrix. For the third row, we leave that one alone, so we've got 0, 0, 1, 0. For the last row, we want to take -1 times our first row and add it to the last row. Well, -1 times our first row, adding it to the last row gives us this row. So y times the transpose of this gives us 1, 0, 2, 0, -1, -3, 0, 1, 2, 0, 1, 2. Okay. Well, our next step would then be to get rid of, so we want to change the sign on the second row. So we're leaving the first row alone, that's just 1, 0, 0, 0, 0. For the second row, we want to change the sign, so it's 0, -1, 0, 0. For the third row, we want to take the second row and add it to the third row, and take the second row and add it to the fourth row. So when we do that, we get another matrix X multiplied by the result that we got out from the first multiplication, and that gives us 1, 0, 2, 0, 1, 3, 0, 0, -1, 0, 0, -1. So one more step, we want to really just multiply the third row by -1 and add it to the last row. We want to multiply the third row by -1. Then we want to multiply the third row times 3 and add it to the second row. So the third row times 3, add it to the second row. And the third row times 2 and add it to the first row. And so we come up with this matrix Z. We multiply Z times our result from that, and lo and behold, we do get our reduced row echelon form there. So kind of putting all of these transformations together, we get Z times X times Y times our T transpose, getting the matrix that we want. Well, our Z times X times Y just becomes the transpose of M. And so what do we have? T times M being the transpose of A, or T times M being A, so that our M looks like Z times X times Y transpose. So what does our matrix M look like when we kind of put all of those together? We get a matrix that looks like this. If we do M times A transpose, kind of our pseudo inverse, what do we get? We get this T with a superscript plus on there. That thing looks like -3, -4, 2, 2, 2, -1, 2, 3, -1, 0, 0, 0. Now this is not going to be a true inverse because things are not really one-to-one necessarily in this case. We're going from 4 dimensions down to 3 dimensions, and so we can't necessarily be one-to-one in that case. More about that later. And so what happens in this case, we can't really talk about the inverse, but we can talk about kind of a pseudo-inverse. It's, for all intents and purposes, it kind of acts like that, but it's not really a true inverse. So remember that our T was going to be this linear combination, and so to see that this actually works, or see how this works, suppose that we wanted the polynomial 3t squared minus 4t plus 5 as some linear combination of t squared plus 2, 2t squared minus t plus 1, t plus 2, and t squared plus t plus 4. How can we do that? Well, we take our coefficients, 3, -4, 5. We make them a vector. And so the identity matrix times that vector gives us the one that we want. But this identity matrix, our 3 by 3 identity matrix, remember this was t times t plus. Well, matrix multiplication is associative, so we can regroup. And so we get t times t plus, or t plus, times that 3, -4, 5, gives us 17, -7, 11, and 0. So t times that matrix, t applied to that matrix, gives us 3, -4, 5. And so what we have there then is this 17, negative 7, 11, and 0 is a linear combination that gives us 3, negative 4, 5. If we want to actually check that out, verify that that really does happen, then we've got 17 times t squared plus 2 minus 7 times t squared minus t plus 1 minus 11 times t plus 2 gives us 17t squared plus 34 minus 14t squared plus 7t minus 7 minus 11t minus 22. Combine all of those terms, and sure enough, we do get down to 3t squared minus 4t plus 5. And so kind of what we see here is how can we really deal with these things with our reduced row echelon forms, matrix multiplications, and kind of looking at things in terms of matrix equations. That's really kind of putting all of these things together to kind of see how it works in a concrete example. Hope that you guys have enjoyed this, and I will see you guys next time.